to answer this question of how to calculate the magnetic field in more general cases, we can actually use some analogical reasoning. If you think about it, we know quite a lot about how to answer these types of questions in the electric field. And hopefully, as we've been learning about the magnetic field, you've been noticing that the electric field case is very, very parallel to the magnetic field case. For instance, there's a force law that gives us the force due to the electric field in terms of the charge. In this case, no velocity is necessary, and then the electric field itself. So the first thing we notice is that there's a very close analogy, except that velocity enters in the magnetic field case, and also we have this cross product instead of an ordinary product. In the electric field case, we actually do know how to calculate the electric field. The electric field at any location R can be determined by summing over all of the particles in the system. So there's a sum over all of the charges I. And then you can write it in various forms. We prefer the Cartesian form. The charge Qi times the vector difference between the location R, where you would like to know the electric field, and R sub I, the location of our particle. That then is divided by the fundamental constants, 4 pi epsilon naught. And then it goes like 1 over distance cubed on the bottom because I have a power of distance on the top. So this would be R minus Ri cubed. Very good. Now, we also happen to know, if I want to continue this analogy, the answer for a very similar analogous situation to this wire. We happen to know that if we have a positive wire of charge density lambda, we happen to know actually what the electric field would be at a distance r above that wire. And the electric field in that case, we know, would be directed straight upwards, like so. And it would have a magnitude E, which looks quite similar, actually, to the magnitude form that we find for the magnetic field in this wire case. In this case, the electric field turns out to be lambda, divided by, then, the combination of constants that we get from Gauss's law, 2 pi r times epsilon naught. So there seems to be a pretty deep parallel between the electric case and the magnetic case, particularly for the situation where we have a wire. But also we see there's a lot of analogy going on here between the formula for the forces. And so that really begins to open the question whether the formula that determines the magnetic field for us would be similarly analogous. For instance, we most certainly would expect that to calculate the magnetic field at a given location R, there should be individual contributions coming from each of the charges, just as there is in the electric field case. So I would imagine it would have some set of contributions, one from each charge. That contribution, it would be sensible to think it would be proportional to the charge, of course, so there should be a factor of Q sub I. Moreover, we know, at least from our final answer for the long wire, that the magnetic field is proportional to the currents that are flowing. And from our previous considerations, we know that current is closely related to these sums over Qi times Vi. The charges times the velocities basically tell us something about the currents, because for currents to flow, you need charges at a certain density, of course, but traveling with a given velocity. So we may also expect that there is some velocity factor involving the charges. But then what we don't know is what else there might be, right? There's probably something analogous to what's going on in the electric field case. After all, we get very similar answers. And if you think about it, that, of course, is not a coincidence either, because remember, it was really relativity that led us to the form for the magnetic field, where we noticed that in the moving reference frame, there was exactly this situation of a long line of charge carrying a long line carrying a certain net charge. So it's very natural to think that this QI-VI product should be multiplying something. We just don't know what it is that it would be multiplying. And that really is what we would like to try to reason our way to uncover in this particular lecture.